In this video, we're going to talk about domain and range. Now, we did kind of briefly talk about this when we discussed functions, but let's go ahead and formally define the domain and range. So the domain, let me go ahead and scroll the screen down a bit. The domain is the set of all input values of a function. Whereas the range is the set of all output values. Which means, based on what we talked about previously, output values of a function, sorry. Let's say the same function because they're connected. And the reason they're connected is they're still the independent and dependent variable as well. So the range is dependent on the domain. Now there's some concepts that go pretty complicated in math with domain and range, but we're going to kind of discuss the general concepts for domain and range, input, output. So let's see, when sending a letter through the United States Postal Service, the price depends upon the weight of the letter as shown below. Determine the domain and range. Okay, so I think it kind of makes most sense to talk about the idea of independent and dependent in this case. And I can't help but feel like the price is dependent on the weight, right? Which to me means that that's our range. Oops. And then the domain would be the weight. Now I want to take that a step further, just rather than labeling domain and range. I actually want to talk about what values the domain and range would kind of be. So when we're looking at the weight, I know that in this table, we're saying that the weight's from 1 ounce, 2 ounce, 3 ounce, and 3.5 ounces, but that's not always what the weight is going to be. You know, the weight of a letter isn't going to just always be exactly 1 ounce. It could potentially be over an ounce, like 1.5 ounces. And if it's 1.5 ounces, that means you'd go into the next category because it says the weight is not over 1 ounce, 2 ounce, 3 ounce, or 3.5 ounces. So technically, in this scenario, we're talking about the weights of letters anywhere from, you know, a tiny amount up until 3.5. So in this case, a nice way of expressing the domain would be to say that the weight, so here we'll use the a W to represent weight, and then here we'll use P to represent price. So I could say that W would need to be bigger than, or actually here, let me say it this way. Technically, it needs to be bigger than or equal to 0. Nah, 0 doesn't make sense when you're talking about weight, right? Because a letter isn't going to weigh 0 ounces. If it did, it wouldn't exist. Okay, needs to be bigger than 0, but smaller than or equal to 3.5 in order to use this price scenario. Okay, that would be the way we can express it as an inequality. Now, if you haven't watched or you don't remember interval notation, I do have a video on interval notation. You may want to go watch if it's been a while. But in interval notation, that would mean we could write it from 0 to 3.5. Oops, sorry. It should be parentheses at 0 and bracket at 3.5. Parentheses because it's not going to equal 0. 3.5 can equal 3.5. All right. So let's talk about the range. Now, in this case, the range is not a range of price. In other words, the minute it jumps up to 1.5, it's going to cost you 71 cents. If you get up to 1.8, it's still going to cost you 71 cents. So those are the set prices for this table. And therefore, the price is going to be 0.5, 0.71, 0.92, and 1.13. You can include the dollar signs on these. I didn't include ounces when I talked about weight, so I'm not going to include it. But I am going to include a special notation. Whenever I make a list of values like this that all go together, I'm going to put it in the squiggly brackets, and that's because this is considered a set. a set of numbers. So the price is going to be one of these four values, either 0.50, 0.71, 0.92, or 1.13. Now that notation is actually called set builder notation, which kind of leads us into our discussion about a different type of notation we're going to look at in college algebra. So we're going to use interval notation, but set builder notation is something that's going to start popping up too, and we want to be familiar with it. So set builder notation helps, especially if you're working with inequalities. It's kind of a natural fit for when you're talking about inequalities. So for instance, if we're talking about an inequality where x is bigger than or equal to 10, but less than 30, in set builder notation, it's going to look like this, the squiggly brackets, but this part at the beginning is telling us what the variable is that we're defining. And as you can see, it says we read that it's x is representing the set of, and then we're telling a restriction. So the set of all x values that are bigger than or equal to 10, but smaller than 30. That's set builder notation. So let's look at how that kind of plays out when we're looking at different types of inequalities. So let's do set builder notation. We kind of did it for the range, but let's do it for the domain for the previous example. So the domain was, sorry, for the W, it was bigger than 0, but less than or equal to 3.5. That was the weight. Okay, so in set builder notation then, I would add a bar to say that I'm defining all the values of W, and then put the set notation around it. And that's the set builder notation for defining the domain. And then we already had the range. I'll just rewrite it. The list of values, 0.5, all the 0, 0.71, 0.92, and 1.13. So there's the way we'd write the set builder for the range if there's just specific values. Okay, so they give examples where we see it with the inequality and interval notation. So here's the inequalities here in this left column, and then there's the set builder notation. And as you can see, all they're adding to each of them is this statement at the beginning. Now, the difference is this example, and I just realized that they didn't carry over for some reason. That little square box is not part of the set builder notation. The set builder notation would have included what's called the real numbers. That's what we use to represent the real numbers, an R with kind of a funny bar. All right. That's the set builder notation there. But other than that, the set builder notation is kind of boring, right? It like just basically adds the H and the bar in front to tell us that we're defining what H looks like. The interval notation is a lot simpler to write, which is why, in my opinion, it's the superior notation. I'm motivated to use interval notation more frequently because it's usually quicker. There are exceptions. And when there are exceptions, that maybe set builder notation will work. But we might work with both notations in this book, and you should know both going forward. I will, however, personally tend to favor interval notation. Okay, now they do mention that it's possible to have two sets or two pieces of information that we want to combine together, like in this example here. So if I wanted to write this in interval notation, we talk about this, okay? The first set of numbers from 1 to 3, I would write as bracket 1, 3, close bracket, because both of those numbers are included in the set. And then the second set of numbers from 5 on, I would do a parentheses. 5 is not included. And since it goes on forever, it goes to infinity. And I always use parentheses with infinity. And then I'm going to put a union symbol because I'm saying that both of these are occurring on the same number line. So that union symbol indicates that they're occurring on the same number line. Okay, so in set builder notation, we would write these as two inequalities. So the first one, when you're saying that it's between 1 and 3, we would write it with the X trapped between the numbers 1 and 3. And then I'm using equal to signs on the 1 and the 3. And then also X is bigger than 5. So we use the word or because both of them are being included on this number line. It's numbers between 1 and 3 or bigger than 5. And then in set builder notation, we would do the X bar and the squigglies. So here's the interval notation and here's the set builder notation. All right, so let's look at graphs and pull domain and range. So we're going to practice domain and range, writing interval notation. And I think we'll go ahead and write set builder notation too, just to practice both. Okay. So let's look at this. Okay. So for the first graph, I'm going to start with interval notation just because I feel it's a little bit easier to start with. It looks like, so when we're talking about domain, we associate domain to be our X values. And then range, we associate to be our Y values. So on this first graph here, I notice that the X values, that's the horizontal line, right, are ranging from -3, so I'm going the furthest to the left, and then up to 2. So from -3 to +2, that's my range of X values. So here, let me do that in interval notation. So from -3, and I'm going to use a bracket because it's a closed circle, comma, 2, parentheses, since it's open circle, and that's the domain. In set builder notation, that would be X is between -3 and 2 with an equal to bar on the 3, but no equal to bar on the 2. And then we'll put the X and the squigglies. Okay, so there's the two notations. Let's do range. Now range is the Y values, and that's the vertical axis. So instead of looking left and right, we need to be looking up and down. How high values go and how low the values go. So in this case then, here, let me do it in green, kind of give it a different color to focus on. Our lowest value is -5, and then our highest value is going to occur at 4. So our range is going to go from -5 with a bracket again. It's got a closed circle there, and then 4, and it's a bracket too, because technically, even though there isn't a closed circle, since it's on the graph, we can assume that that point is closed, right? It would need to be actually an open circle for it to not be included. So there's our range. And then in set builder notation, we're going to switch to Y values because we're talking about Y values now. So ranging from -5 to 4, and then we would be using equal to on both. All right, let's look at the next example here. So starting with domain, so left to right. So the furthest left it goes is 4, the furthest right is 8. So the domain is ranging from 4 to 8. And then because there is a closed circle at 4, it would be a bracket, and then 8 would be an open circle again. So it's a parenthesis. Sorry, I'm trying to make it look more parenthesis-ish. There we go. All right. Let's do the range real quick, and no, let's do the set builder notation. Okay, so set builder notation. So X such that. Okay, so it's between 4 and 8. So we'll start with the 4, less than or equal to X, less than 8, no equal to bar. All right, let's move to the range. So the lowest value is 2, highest value is 8, but in this time 2 is an open parenthesis, whereas 8 is a bracket. So the set builder notation for that would be Y such that 2 is less than Y, less than or equal to 8. All right. Now let's do the domain and range for all the toolkit functions. And I'm going to just do interval notation for these. There's nothing wrong with both. I just want to go ahead and focus on interval notation because it tends to be a little bit quicker. And then, yeah, we'll kind of go back and talk about later. Okay, so for the constant function, we referred to f of x equaling 2. In this function, the domain is going to the left forever and to the right forever. So it's all real numbers. And in interval notation, we would use negative infinity to positive infinity to do that. The range is actually only one value. It's 2. It's always going to be 2. So when we write a single number, there's a couple ways to do that. But one way is to go ahead and do a bracket with the 2 and close it. That's one way. You could switch to set builder notation. A lot of people don't do that. Interval notation for a single value like that. It's not as common, but the author of this book feels like it's a good way of kind of handling a single number. All right, let's do domain for the next one. Again, it's going forever to the left and forever to the right. So all real numbers or negative infinity to positive infinity. The range is actually going all the way down and all the way up, right? It's forever going down. There's no low point, no high point because of the arrows, right? So the range is also all real numbers. Okay, absolute value function, forever to the left, forever to the right. Hope you guys are seeing there's a bit of a pattern here. Not very much restrictions. The range, however, it does go up forever, but it does have a low point. The low point is right there, right at 0. So the range is going to go from 0, and it's closed because it's on the graph, to infinity. Notice we always use parentheses with infinity, right? Because infinity is not a number, so we always use parentheses. All right, let's look at the quadratic domain. Now, even though it's not as spread out as the last graph, there are arrows, and that's implying that this parabola is expanding to the left and to the right forever. And therefore, it is from negative infinity to positive infinity. Just like the last graph, though, the range is limited. Switch to green. We have a low point, again, at 0. So 0 to infinity would be the range. Okay, again, even more narrow, but the arrows are indicating that they're going to keep going a little bit to the left, and a little bit to the right forever, which means it's going to keep expanding out forever. So negative infinity, positive infinity. And then the range would be also negative infinity, positive infinity, since it's going up and down forever. Square root function. This one's finally exciting and different. It does have a far left value. Its furthest left value is right here, right at 0. It's starting at 0, but then it goes on forever to the right. So infinity. Oops, I put an R and it should have been D. All right. Then the range is starting, or I should say, yeah, its lowest point is 0 again. It is lowest point at 0, and then it is expanding up to infinity. It's just kind of slow. And that point is included on the graph. Just so you know, it's kind of hard to see. All right, cube root function. So expanding left and right forever. Negative infinity, positive infinity. Range is going. It is going up and down. It's just really slightly going up and slightly going down. So negative infinity, positive infinity. Okay, now we have our first 2 graphs where they're even more interesting than the square root function. We actually have an asymptote here at the y-axis and the x-axis. And that's because we're not allowed to plug in 0 for X. All right. And we'll never get out 0 for Y in the reciprocal function. So I can't plug in 0 for X, first of all, because that's going to give me a 0 in the denominator, right? But then I'll never get a 0 out, no matter what number I plug into the denominator. So I actually don't get 0 either for the range. But I do get every other value. Domain does go forever to the left and forever to the right. I just can't have 0. So here's how we indicate that. Goes from -infinity to 0, doesn't include 0, it's a parenthesis, and then union 0 to infinity. So it picks up with starting at 0, but not including it. And then the range would be identical. Okay, so this also has a vertical and horizontal asymptote. However, the range is going to have a limit, right? It's not going to keep going down forever like the last graph. The domain, however, it keeps going to the left and right. So -infinity up to 0, union 0 to infinity, just like the last one. The range, though, is going to not go any lower than 0. So we will pick up at 0 and then go to infinity. But never hit 0 because there's an asymptote there. Okay, now let's do this example for domain and range. And this might be something you've seen in like intermediate algebra, but we're worried about what we're allowed to plug in for X, especially when we're looking at square roots and especially when we're looking at fractions, which we can tell based on the toolkit functions, right? The most interesting examples were the ones with fractions and square root. The rest of them weren't very interesting, okay? So let's go ahead and look at that. So when we have a square root, we know we can't have a negative under the radical. So no negatives under the radical. Otherwise, we're going to get imaginary numbers. So that means whatever's under the radical needs to be positive. So I'm going to write that then as X plus 4 needs to be bigger than or equal to 0. As long as it's bigger than or equal to 0, we're good to go. So let me solve for X. So I'm getting X is bigger than or equal to -4. Now, because I've already kind of solved an inequality, it might make sense to just write the domain as set builder notation. This is me kind of being lazy, and there's nothing wrong with that, but that would be the domain. If I wanted to do it in interval notation, basically it's all numbers bigger than or equal to -4. So interval notation, that would be from -4 to infinity. Now, just be careful on the homework. They'll probably indicate which way they want you to enter the answers. Most likely it's going to be interval notation. It's just the most popular of the two. Okay, so for part B, we have to have zeros in the denominator. So no 0 in the denominator, which basically means I'm going to take the denominator and say it can't be 0. So let's solve. Minus the 6, divide by -3, and I'm going to get that X cannot equal 2, which makes sense if I plug 2 and I'm going to get 0. So for set builder, we can do this. Interval notation, though, we would have to actually do the skipping thing that we did with the functions above. We would have to go from -infinity to 2, union 2 to infinity. In other words, we're excluding including everything, but we are excluding the 2. And that's how we could write that in the two notations.